Okay, today is November 14th, 2011. We're on lesson 5.2. We're working with determining rates of change. Our formulas are underneath here. So we're pretty much working with linear equations, which are straight lines on the graph. And rates of change deal with the slopes of those lines. So our first equation we have, y equals mx plus b. That's the slope y-intercept form of a linear equation. So remember, m is our slope and b is our y-intercept. And the equation underneath is how to find slope. We have m is equal to y2 minus y1 divided by x2 minus x1, which is also equal to the rise over the run of an equation. So what we're going to do first off is we have a question here. It says distance driven in a car is our x-axis. So distance driven. And our y-axis is cost of renting a car. So we're comparing the cost of renting a car to the distance driven. So apparently you're paying when you bring the car back. We need to find the average rate of change. Average rate of change is essentially our slope. It's just what we're looking for there, our average rate of change. So we're going to be looking for the change in height divided by the change in time. Since height of our graph is going to be the cost, this is also the height here, our y-axis, we're looking for the change in height divided by, so we'll put change in y, we'll say, divided by change in x. And that's exactly what this formula is over here, y2 subtract y1. So we're going to get 2 points along the graph. We'll take this as our first point, which is at 300 and 400. And our next point's at 500 and 700. Okay? Okay, so we take those 2 points. We're going to call one our first point and one of them our second. So we're going to call this our first point and this our second point. We're going to give ourselves a little bit of room here. So we'll write our formula down. Our slope, or our average rate, or average change in the height versus the distance driven, is going to be our y2 subtract y1 divided by x2 subtract x1. I'm going to put an m here because we know that's what it's equal to. I'm also going to write my 2 points down. My first point, which was 300 and 400. And I'm going to call that my x1 and y1, just so I know what to plug in. My second point will be 500 and 700. x2 and y2. So when we go to plug it into the equation, our y2, which is 700, subtract y1, which is 400, is divided by x2, which is 500, subtract x1, which is 300. 700 by subtract 400 is 300 over 200, which is 3 over 2, or 1.5. Okay? So the average rate of change is 1.5 or 3 over 2. So what they're saying, let me go back up to make sense of this, is that for every 200 kilometers driven, it looks like our price goes up $300. It's quite expensive for renting the car. Okay? So a rental costs every 200 kilometers driven. That's how far we've gone across. Our distance was 200 here. Our price goes up $300. So $300 for every 200 kilometers driven. That's really expensive for renting. All right, example 2. Example 2. we have speed and reaction time. So what this is a stunt car driver, and they're testing him at certain speeds and how long it takes him to react. So our reaction, oh sorry, this is reaction in distance, not time. So reaction distance, it's being measured in meters, and our speed is in kilometers an hour. Okay? Now what we have to do here is we want to find out if there's a difference in terms of reaction, if his reaction times get faster, slower, or if they're constant depending on his speed. So in other words, what we're doing is we're going to be finding our first differences. Okay? So our first differences, I'm going to make a little chart here for them, is we're going to be subtracting the y values from each other to find out the change for every 10 kilometers an hour difference. So it's important when you guys do first differences, we're always finding the first difference of the y values, but we have to make sure that our increments of x are the same. So in other words, this one's constantly going up by 10. That way we can find first differences. If these numbers weren't going up by a constant rate, we'd have to fix that so that they are. So in other words, first differences, what I'm going to do is I'm going to take 2 and subtract 0. 2 subtract 0 is 2. Okay? Then we take the next number down and subtract the one above. We take 4, subtract 2, 2 again. 6 subtract 4 is 2. 8 subtract 6, 2, and 10 subtract 8, we got 2 again. So what we found is that the change is constantly 2 meters in terms of his reaction time. So for every 10 kilometers we increase in speed, his reaction time decreases by 2 meters. So remember, we have to find what the rate of change is. In order to find the rate of change, we know that the first differences are the number 2, so we know this is going to be linear, this relationship. Now I have to find the average rate of change. Because this is going up by the same amount every time, and this is changing by the same amount every time, we just have to find 2 points. So we're going to find the very first one using our slope. So we're going to take y2, subtract y1, divided by x2, subtract x1. And we're going to use the very first 2 coordinates. First one is 0 and 0. Second one is 10 and 2. We'll call this coordinate 1 and coordinate 2. So we have x1, x2, y1, y2. So y2 is the number 2. Subtracted by y1 is 0. Over x2 is 10. x1 is 0. We end up with 2 over 10, which when we divide it is 0.2. So another way we can tell if we have a constant rate of change is to find the first differences between all of the y values. And then to find it, we again put in our slope formula. The average rate of change was 0.2 meters per second. Yeah, for every increase of 1 kilometer an hour, he increases by 0.2 meters in reaction time. So his reaction time gets slower and slower the faster his vehicle's moving. All right, in our last example, we have the growth of a tomato plant over weeks in time. So we have all of these coordinates. So again, the tomato plant, we have its growth in centimeters over weeks. Okay? We've plotted it down below. From looking at this, we can tell it's not a linear relationship. This is changing. The rates of change every 2 weeks, it looks like. So if you guys notice the slope, we're going to quickly dot out a few, is constantly changing. On average, it looks like it starts off slow, between the months of maybe 6 to 12, the rates of change picks up a lot, and then finally it completely stops growing, which means it's matured all the way, this plant. What we're going to do is we're going to find the first differences, and then we're going to find the rates of change. Okay. So, first thing we're going to do is we're going to find first differences again. When we find first differences, we can actually use those numbers to determine the rates of change. The first differences are essentially the differences in y2 and y1 for all of our coordinates. So we're essentially finding the top half of our slope formula. So remember, our formula again was y2 minus y1. That is first differences. So once you've found the first differences, you've actually found the top half of the equation for our slope. So we're going to quickly find our first differences. And we'll know if it's linear or not. Clearly, we're going to have a non-linear relationship because these first differences won't be the same. So we take 5 from 0, and we end up with 5. Then we take 10 from 5, end up with 5 again. 20 from 10 is 10. 40 from 20 is 20. 58 from 40 is 18. So it's slowed down. 75 from 58 is 17. 86 subtract 75 is 11. 90 from 86 is 4. And finally, 90 from 90, there is no change in those. So if we notice, all of our, well, for the most part, our first differences have changed. They've also told us quite a bit about the slope of this. Because our x differences are the same, they're constantly going up by 2. What we know we can do here in order to find each of the rates of change is we just got to take our first difference and divide it by 2, since 2 is the difference between x2 and x1 for all of these numbers. So I'm instantly going to find the rates of change. I'm going to put them in red by just taking the number and dividing by 2. So our very first one, 5 divided by 2, we got 2.5 as our rate of change. So we got 2.5 for the first one. Our second one is the exact same number. We'll get 2.5 again. We take 10 divided by 2. We get 5. 20 divided by 2 is 10. 18 divided by 2 is 9. 17 divided by 2 is 8.5. 11 divided by 2 is 5.5. 4 divided by 2 is 0. And 0 divided by 2 is 0. So, by finding the first differences, we are able to speed up our rates, our average rate of change between each of our coordinates. We found out that it slowly took off, picked up in speed, 5, 10, 9, decreased, and finally matured all the way. So, what we've done between the two of these is, in our first example, we had a constant. Don't worry.
Oh my God, what?
Constant rate of change. Okay? And in our other example, in our second example, we had a changing rate of change.